Hello, everybody. It's a pleasure for me to be with you today and to talk to you about greenhouse gases. The title of my talk is the 2050 Challenge, Feeding the World Without Wasting It. My name is Frank Mitloehner. I'm here at UC Davis. I have been here since 2002. Time flies. My Twitter handle is GHGGuru, stands for greenhouse gas, and please follow me. I also write a blog, clear.ucdavis.edu/blog. So first, I just want to talk about greenhouse gases for a while. There are some really interesting new developments in and around livestock/poultry on the one side and impacts on greenhouse gases and carbon footprint. That's such a hot topic that I think is quite relevant to everybody in animal agriculture. So what are greenhouse gases all about? So greenhouse gases are gases such as CO2, methane, nitrous oxide, and others, and they pretty much form a blanket over the Earth's atmosphere. Okay? So now imagine the sun, which radiates solar beams to the surface of the Earth. Normally, those solar beams would be reflected back into space if there weren't these greenhouse gases keeping the solar heat back in our atmosphere. So it's pretty much like a blanket over your body, on a cool summer evening, retaining your body temperature close to your body. These greenhouse gases do pretty much the same thing. So again, carbon dioxide, methane, nitrous oxide, there's some others, are these greenhouse gases. And while most climate scientists will say that carbon dioxide is the most important one, particularly people in the anti-livestock arena say, oh no, methane is the 800-pound gorilla. I will talk to you for a while now about methane. Methane is the Achilles heel of animal agriculture when it comes to climate. How is methane compared to other greenhouse gases? Well, there's a 30-year-old unit that's called the global warming potential, in short GWP 100. And this GWP 100 allows you to convert the impact of methane and nitrous oxide, which are more potent than CO2, to CO2. So this is how this works. Let's say you were to have a farm and your farm produces 100 tons of methane. Then all that needs to be done is you take the 100 tons of methane from your farm, multiply it by this factor, the so-called global warming potential factor. And when you do that, the 100 times the 28, then you arrive at the total amount of CO2 equivalent gases. So 28 is the factor that you have to use to convert something into CO2e, CO2 equivalent units. Okay, the same is true for nitrous oxide. If you have a farm and you produce, let's say, 10 tons of nitrous oxide, all you need to do is multiply the 10 times this factor, 265, and then you arrive at the CO2e, CO2 equivalent amount of greenhouse gas from that 10 tons of nitrous oxide. This is how it had been done for decades, and in my opinion, particularly for methane, this is not the way to go. There's no doubt, and I want to be very clear about that methane is a potent greenhouse gas. But there are other nuances to this discussion that are generally ignored. This slide here shows the global methane budget. You see on the left side of this slide various sources of methane: fossil fuel production and use, agriculture and waste, and so on others, amounting to globally 560 teragrams of methane that are emitted into the atmosphere. So these are the sources. And then most reporting that we see in the media does not report on the other side of the budget, because there is a second side, and that amounts to 550 teragrams. And these are the sinks. So there are sources on the left side, 560, and there are sinks on the other side, 550, meaning there are significant processes by which methane is destroyed. And that leaves not 560 teragrams in our atmosphere, but 10. That's the difference between sources and sinks. So what is this important process that kills methane? You see it underneath this large arrow that's pointing downward. It says sink from chemical reactions in the atmosphere. So when methane is in the atmosphere, within 10 years, it meets another molecule called a radical. And this radical steals hydrogen away from the methane, killing it. So after approximately 1 decade, Methane is no longer in the air. At least the vast majority of it isn't. So it's very important to understand methane is not just produced, but methane is also naturally destroyed. And that destruction is called an atmospheric removal. Atmospheric removal. Okay, remember that. So this atmospheric removal leads to the fact that methane has a very short lifespan, while CO2 and nitrous oxide, once they are emitted and in the air, live there for a long time. In the case of CO2, 1,000 years. Methane is not just produced like CO2, but methane is produced and destroyed almost at equal rates. Almost at equal rates. And that is not just a small little nuance, that is essential in our understanding of methane and in our accounting of that gas. I will show you a bovine here rather than a chicken, but it's the same principle applies to poultry that applies to cattle, let's say. So have you ever wondered what methane, which is CH4, um, where the carbon in that methane, where it originates? Well, it originates in the atmosphere. And it starts, this whole process I'm now talking about, starts with our plants. What do plants need to grow? They need sunlight, they need water, and they need a form of carbon. And that form of carbon is CO2. That carbon during photosynthesis makes it into the plants, and then the plants either produce cellulose, and that's of course essential for ruminants, or starch. That's of course then also consumed by all the other livestock poultry species. So and that carbon is now then in the plant material, and the plants convert it into carbohydrates, as I said, cellulose or starch or so. Now the animals come along, they eat this stuff, they eat the carbohydrates. In the case of ruminant livestock, they belch some off, belch some out, coming out the front end. Some more methane comes from the animal manure. And that's also applicable, of course, to poultry because their manure also produces methane, like the manure of all livestock and poultry. This carbon contained in this methane is not new carbon added to the atmosphere. Instead, it's recycled carbon, which originated in the form of atmospheric CO2. So the carbon in the methane from constant herds of logs is nothing other than recycled carbon that was in the atmosphere originally. And after approximately a decade, that carbon becomes CO2 again. The process that destroys the methane is called oxidation. To be precise, it's called hydroxyl oxidation. And so you will now say, well, why is that a good thing? Methane, you just said, lives only 10 years, CO2, 1,000 years. It's not a question whether this is a good or bad thing. The question is really, does a constant number of livestock or poultry add additional new carbon to the atmosphere? Additional new carbon to the atmosphere. And the answer to that is no, they do. They do not. They do not. They are recycling existing carbon. While that methane from constant herds is in the atmosphere, it causes warming, but not additional warming. It maintains current levels, not additional warming. This is really different from, let's say, fossil fuels, oil, coal, and gas. And I will explain that in a minute. So on the livestock side, whether it's cattle or whether it's pigs or whether it's poultry, these animals all have one thing in common, and that's they eat plants. And while the plants were growing, they took carbon out of the air. They then produced feed for livestock and poultry. Our animals ate that plant material and then released some of the carbon back into the atmosphere. Some of it stays in the form of CO2, of CH4, but only for 10 years, and then it's reverted back into CO2. This is very different. This greenhouse gas process here is very different from the one associated with oil, coal, and gas, the so-called fossil fuels. What are oil, coal, and gas? That's pretty much ancient forests and ancient animals. They died, they decayed, they fossilized. And then they accumulated down there for a long time until humans came along, and over the last 70 years, 70 that is, we have extracted half of all of that fossil fuel. We extracted it from the ground. And what did we do with that carbon? We burned it and then added it to the atmosphere. And that, ladies and gentlemen, is the main culprit for human-caused climate change. This here is not a cycle. This is a one-way street from the ground up into the air. And this is why we see global CO2 levels rising, 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 and rising. So really quickly, a comparison between a gas like CO2, which you produce when you drive your car, for example, when you burn gas, versus methane. So CO2, let's say you drive your car on Monday from home to work. When you do so, you put CO2 into the atmosphere through the tailpipe of your car. On Tuesday, you drive again, and now you put the same amount of CO2 into the atmosphere, which is then on top and additional to what you put into the atmosphere on Monday. On Wednesday, you drive again, and as you can see, you add new CO2 to the existing stock from Tuesday and from Monday, and from last week, and from last month, and from last year, and from the last decade, and from all of the stuff that your parents and grandparents put in the air, okay? So every time we burn fossil fuels, we add new additional carbon to the atmosphere. And that's what makes CO2 a stock gas. It accumulates in the atmosphere. In contrast to that, methane is to be discussed now. Methane is treated by agencies and so on as if it were to do the same thing, accumulate in the atmosphere, as if it were to build up over time more and more and more. But is that true? And the answer to that is no, because there is an atmospheric removal process, this oxidation process I talked about earlier. Methane stays in the atmosphere for 10 years. If the source of methane is constant, for example, a constant flock or constant herd of livestock, then they are producing a constant amount of methane, and that means the same amount of methane that's produced equals the amount of methane that's destroyed. I give you a really quick analogy. Imagine two bathtubs. The first bathtub is the analogy for CO2. This bathtub has only a faucet, but no drain. You turn on the faucet, it doesn't matter whether it's turned on a little bit or all the way. And what happens to the water level is it rises. It can go only one way because there's no drain in that bathtub. It rises. That's what CO2 does. Now comes the other bathtub, the methane bathtub. Now you have a faucet putting in water into the bathtub, but you also have an open drain releasing that water at the same rate. So what happens when you put in water with your faucet, but you release it at the same rate, is that the water level will stay stable and constant. If you crank up the faucet all the way, then the levels will rise, even though the drain is open. And we don't want to see that. And in parts of the world, we do see that, where livestock and poultry herds grow drastically in the third world, for example, and that leads to new additional methane. We don't want to see that. Okay? We want to keep methane stable, or even better, we want to decrease it. So what happens if you decrease methane? The analogy again, our bathtub, we are now turning the faucet down, so water is still going in, but not at the normal rate, at a lower rate, and the drain is still open. And that means now there's more water drained than refilled, and that means the levels go down. Okay, so that's the analogy for CO2 and for methane, and I hope you remember that. I will now give you three scenarios and show you how this unit GWP 100 that's currently being used to quantify methane's impact on climate, how that's really off and why its use is wrong. Three scenarios. The first one is one where methane over 30 years increases by 35%. The second one is a scenario where methane is pretty stable, or we slightly reduce it over 30 years by 10%. And the third one is a scenario by which we decrease methane by 35%. How are these three, or how would these three scenarios, the increasing, the stable, and the decreasing amount of methane in the atmosphere, be characterized by using this GWP 100? This GWP 100 would predict the increasing, the stable, and the decreasing amount of methane as a strong increase of CO2 equivalent emissions. All three of them would be depicted as if the methane would add to a significant increase in CO2 equivalent units. But that's not true, because it does not take into consideration the atmospheric removal of methane, the natural atmospheric removal of methane. which in the case, for example, of a stable scenario, should really have production and destruction in balance. So let's go to the top here. The new unit that's proposed by colleagues from the University of Oxford in the UK, it's called GWP star, does agree with the GWP 100 that if we increase methane strongly, then that indeed has a strong impact on warming of our climate. We don't want to see that. And in parts of the world, we do see it. In most part of the developed world, we do not see it. So in the US, we don't see it. In Europe, we don't see it. But in parts of the third world, we do see it. But look what happens when you slightly decrease methane. When you decrease methane, then there is no blue north of the x-axis, meaning there is no additional warming occurring from a stable or slightly decreasing methane source. The amount of methane produced and the amount of methane destroyed are in balance. Now you see a negative sign in front of the number, meaning there's not positive warming like on the center here, but there's no negative warming. And that's actually a fancy word for cooling. If you decrease methane strongly, then you don't have any additional greenhouse gases emitted in the atmosphere, like GWP 100 would suggest, but you have a strong removal of greenhouse gases from the atmosphere. Much like planting trees. If you plant trees, then those forests, those trees would take CO2 out of the atmosphere, and that has a cooling effect. If you reduce methane, for example, by using anaerobic digesters for your poultry operations, then you can reduce carbon. You can even produce carbon negative fuels by making biogas from animal manure into renewable natural gas, which can then be used to run vehicle fleets. This is actually something we do now in California at a major, major scale, converting biogas from animal agriculture into a fuel type. And we have already achieved here in California a 25% reduction of methane over the last 3 years. 25% reduction of methane, excuse me. So we are already in this scenario over here to the bottom right. I will now talk to you about the so-called 2050 challenge, one that's of global significance. On the x-axis here, you see the year 1750 to 2050, hence the name 2050 challenge. And on the z-axis, you see the human population in billions. I'm in my early 50s. When I was a little boy, we were right here at 3 billion people. Today, we are at 7.6 billion. And by the time I'm an old man, we'll be at 9.5 billion people. Human population on this planet will have tripled throughout my lifetime. Tripled throughout my lifetime. Interesting here too, the developing world is depicted, the developed world is depicted in orange. That's the Americas and Europe and parts of Asia, where human population is plateauing. But look what happens in the developing world. Human population is exploding, largely a function of increasing life expectancy in these countries. This is a photo of the world, and it shows a circle over Southeast Asia. And this circle here contains more people in it than the rest of the world combined. Think about that for a second. This circle contains more people in it than the rest of the world combined. Clearly an area of food insecurity within future generations, but not the only one. While Southeast Asia will increase human population by 40%, Africa will increase by close to 50%. So the 2050 challenge is really one of these, or in these two major regions. The Americas will slightly increase, Europe will shrink, but it's all about parts of Asia and mainly Africa. Meat consumption has grown pretty strongly, particularly in developing countries, in emerging and developing countries. You see here in developed countries, it's pretty much a flat line. But in sub-Saharan Africa, in South America, in Southeast Asia, Middle East, North Africa, and so on, meat consumption is going up. People, as soon as they are lifted out of poverty, will start eating animal source foods at larger rates. This slide here is a map showing where in the world we have cropland. And so while we have a tripling of human population in the world, we're very limited with respect to the amount of land we have to grow food for these people. And this is why sectors like yours is under increasing scrutiny now, where people who are plant-based advocates say we should stop producing animal source foods and only produce plant-based foods. because animal source foods need too much land and so on. Statistics here from the dairy side of things, but the same applies to poultry. This slide here shows on the x-axis milk production per cow per year, and on the y-axis it shows the carbon footprint per unit of milk produced. Each dot here shows one country in the world. Okay, so these are 200 countries approximately. You see many countries have cows producing a dismal amount of milk, about 1,000 pounds or so of milk. That's 500 kg, 500 kilogram. In the United States, a cow doesn't produce 1,000 pounds, but 23,000 pounds, similar to Canada, 23,000 pounds. So it takes about 20 times the number of cows in these countries to produce the same amount of milk as one cow here in North America. And that has a profound impact on the environmental footprint. The same is true for poultry, the same is true for pigs. Production efficiencies and environmental impact are inversely related. The relatively more productive our livestock and poultry is, the relatively lower is the environmental footprint. That's true for carbon, it's true for nitrogen, it's true for everything else. In much of North America and Europe, we have learned to improve productivity and optimize it through improving fertility, reproductive rates, establishing a veterinary system of preventing or treating diseases, improving genetics, it's a big deal, and of course also by feeding more energy-dense diets. These four main factors have allowed us to shrink the number of animals used in our respective countries to historic lows. Here a depiction of a broiler scenario from 1925 till predicted 2045. You see here the advances around conversion efficiencies, mortalities, the age of the broilers, and the live commercial weight. These numbers are not new to you, but these numbers are new to much of the population you're dealing with. And they might think, nah, I don't like to see that. I would rather have a slow-growing bird. And there are actually trends now to reintroduce slow-growing birds. I think people need to understand what that means. If we were to reverse this trend, we would make our livestock and poultry less environmentally efficient and more polluting. We do not want to reverse this trend. We should be proud of what we have achieved. Okay, this is a huge animal welfare advancement, as you can see on the mortality, as well as an environmental advance. So certainly not something I would like to see going back. I apologize for the bad resolution here, but I can't help but show how our broilers have changed from historic till present levels. There's some people who say we need to change what we eat. Never before have we eaten more meat. Well, that's only partly true. In the United States, for example, between 1909 and pretty much today, we have had very stable red meat consumption. Okay, beef and other red meat, very stable. What has increased, and pretty drastically so, is chicken meat. We are now eating 500% more chicken in the US than we did in 1909. So that is really what you are doing, is really the big winning commodity when you compare it to everything else. Red meat has not really changed much. We have all of our special friends within PETA and HSUS and so on, trying to get people to be anti-animal agriculture. They're oftentimes using global warming as a reason why people should stop eating meat or eggs or milk and other dairy products. They use welfare arguments and so forth. But the environmental argument is gaining momentum. And I think that even though beef and dairy are more in the crosshair, all livestock and poultry commodities are being criticized in a major way. So because of that, I threw a slide in with the question, can we eat our way out of climate change? Some people say, the activists say we can. So let's say you were an omnivore and for climate reasons you were to decide to go vegan for 1 year. What would that do to your carbon footprint? It would reduce it by 0.8 tons of CO2 equivalents. 0.8 tons. So is that much or not? Let's compare that to a single one-passenger flight from North America to Europe, which would amount to 1.6 tons of CO2 equivalent. So going vegan for 1 year would have half the impact of one flight per passenger to Europe. A meatless Monday for the entire United States would reduce the greenhouse gas impact of the US by 0.3%. Going vegan as a nation would reduce the carbon footprint of the United States by 2.6%. These numbers are very similar to those in Canada. So the notion of all we need to do is change what we eat and that will halt climate change is nothing but nonsense. Okay, it's absolute nonsense. And the reason why I have a beef with that is because it sets us on a wrong track for solutions, a wrong path to solutions, because by far the use of fossil fuel is the main culprit of humans' impact on climate. In countries like yours or mine, at least 80%, 80, of our emissions, greenhouse gas emissions, are associated with the use of oil, coal, and gas, whether we like it or not, but that's where the main culprit sits. In the US, all animal agriculture combined amounts to 4%. And in Canada, it's very similar. So just know that. So 2 more slides and then I'm done. Those people who say we should all start eating and only eat plant-based foods are oftentimes quite concerned about their own narrative. Why? Because 84% of vegetarians and vegans abandon their diet after 1 year. For every one active vegetarian and vegan in the United States, there are 5 former vegetarians and vegans. I'm not saying that to make fun of them or something. I'm saying that only because that dietary regimen is oftentimes described as being more sustainable. Well, a dietary choice that is abandoned after 1 year is not very sustainable. If it were, people would stay with it, okay? And they don't. The overarching majority does not stay with it. If you were to be interested in knowing what the biggest impact of our food system is, from cradle to grave, then by far, the number one is depicted on this slide. This is from the National Geographic. It shows a average US family in front of all the food waste associated with its family. 40% of all food produced in the United States, produced in Canada, produced in Europe, 40% of all food produced goes to waste, goes to landfills. And what I find stunning is that not just is the 40% number true for the developed world, it's even true for the developing world. In, let's say, African countries, it's also 40%, but they're not so much at the consumer level, like here, but there it happens at the producer level, because people can't harvest on time, they can't transport their products, their produce to the markets, to the distribution and processing plants, and so on. 40% of food waste is a number that is unacceptable. It's globally applicable right now, and I think we can all do better. We should do better. But all of that really requires that, first of all, we have some honest and sincere discussions around our food. One that's not in an antagonistic way where we fight each other, but one where we treat those people growing that food that we all eat with respect. Our farmers deserve that respect. And I will always be that person working with people in agriculture to find out what the environmental footprint is and where it's a problem, finding ways to improve it, because that's how we make progress, and not by chastising them and so on. So with that, I thank you very much for your attention, and I'm very happy to entertain any questions that you
Well, there's always lots of questions, Dr. Frank, after you speak. And I know we've had a couple just blown away by the great facts that you're presenting and asking about whether this presentation was available again later. And just a reminder to all of registrants that these presentations will be available later in the week. So you'll get a link and be able to access them again, because I think they want to share it with family and friends, and maybe those that they have this discussion point with, because certainly very eye-opening as always. So thanks for sharing that. We've had a couple questions come in already, Frank. What does atmospheric CO2, or rather, why does atmospheric CO2 have such a long half-life when it really is a component of plant respiration and is captured naturally into plant-based carbon?
Yeah, so these are two separate questions. So first of all, what plants do with CO2 has nothing really to do with its lifespan, because it's true, of course, that plants take on CO2 to grow and produce, let's say, carbohydrates such as cellulose or starch. But once the plants die, that carbon will be released back into the atmosphere. So it's kind of a wash. And that's even true for trees. Even though when it comes to trees, of course, the question is always what happens to the trees once they are taken down. If they catch on fire during a wildfire, then that carbon that these trees had assimilated and sequestered will go into the atmosphere right away. If it's a grass fire, then that grass carbon will be released right away. So with respect to the lifespan of this gas of CO2, there's just no atmospheric removal process of major proportions. There is one for methane, destroying methane, making it into CO2, but there is no such thing for CO2 itself.
You know, as a communicator, it's always interesting seeing how sort of this misinformation gets blown up. But why do you think methane became such a bad boy? Is it easier to blame cows and pigs and chickens than to take away our fancy cars or our regular cars? Why do you think methane became such a bad boy in this whole debate?
So methane is a bad boy. Methane is a potent greenhouse gas, okay, and we do not want to increase it. We don't want to grow flocks and herds and so on, leading to additional methane. But we want to keep our current methane stable or even decrease it. If we increase it, we have new additional warming. We don't want that. So it is a bad boy. It is almost 30 times more potent than CO2, but it is very different from CO2 and very different from other greenhouse gases. If we manage it well, it can even provide us with an opportunity for cooling. And so why is it being used? Well, it's being used because there are people who don't like animal agriculture very much, and they view that as probably the Achilles heel in animal agriculture. It really is the Achilles heel on the environmental side currently, and it has been used as such for years now. So it is very important for you, whether you are directly related as a farmer with agriculture, or whether you are in the supply chain somewhat, that you understand the nuances around this gas in contrast to other gases, because the carbon footprint of livestock and its products, livestock poultry and its products, I should say, is hinged to that gas, okay, that nitrous oxide, that methane gas. The other one, nitrous oxide, by the way, is also very important, but methane is where the majority of the criticism is centered.
So we've just been missing part of the message in terms of the fact that of that balancing factor on the methane there.
For sure. This is really important. I brought this whole topic to the attention of the FAO in Rome, the Food and Agriculture Organization of the United Nations. And they consider the content of what I just provided as being so critical that the FAO established a global task force with 65 of the world's finest scientists to really drill into this topic, okay? How is biogenic methane different from other greenhouse gases? And is it true that if we reduce it, we can induce negative warming, which is cooling? And also, how do we mitigate this, for not just ruminant livestock, but also for pigs, for poultry, and so forth? And there are great opportunities around the corner.
So do you get to serve on that panel? Because you should.
Yeah, I do.
Oh, good. All right, just a reminder again, if you've got questions, just to type them into the question and answer button that you see on the bottom of your screen there. We've got another question here from Ben. When birds eat manure, where does the gas go?
Um, when birds eat manure, where does the gas go? So first of all, the manure in general generates gas, biogas, methane, for example, and other gases. Generally, when it stores for a while, okay, it doesn't just happen instantaneously. So methane generally occurs when the manure is stored for a while. So when the animal eats manure, a couple hours later, that new now digested manure will be excreted again. So it will not go anywhere. It will just be excreted sooner or later. It's just a little bit of a time delay.
Tell us a little more about the great results of things that are happening in California. You mentioned the dairy and some of the biogas that's being used and reduced or reused in different ways, and thus those levels reduced. Are you looking at it for other types of livestock as well, or bring us up to date on some of the progress California's made?
Yeah, so first of all, this is a huge accomplishment to have reduced 25% of methane within 3 years. Means that we are over halfway at our 40% reduction goal. Okay, that's enormous. I don't think that this has been done anywhere else in the world. This general concept of covering a lagoon, trapping the gas, is not new. Okay, it's called anaerobic digestion. That's not new. What is kind of new is to convert this biogas into fuel, because that resulting fuel is the most carbon negative fuel type there is. And carbon negative means you're actually now reducing carbon. You are net reducing carbon, and that is incentivized by, for example, our state, in form of low carbon fuel standard credits. And these credits are so high that this conversion of a regular lagoon into a covered lagoon is very attractive to many. We already have 150 of the largest dairies who have made this step, and many others will follow. In my opinion, within the next few years, most of our dairy lagoons will be covered in the state of California. And I do think most other states will look into this and see if this is a model to copy and paste, so to say. And I think it will be. And I think it will also be very lucrative to other states, other countries, including yours. Is it possible? Is it possible to do that with poultry waste?
Yeah,
Absolutely.
that's what I was gonna ask.
Absolutely. Not just is it possible, poultry manure is a prime candidate for it because of how poultry manure is composed and what it's composed of. You would produce a lot of biogas, for sure. So, one thing is important. In the past, people took that biogas and they burned it to make power. And that is not a good idea. Why? Because it's not lucrative enough. Because power from fossil fuels is too cheap. And this power type cannot compete with a relatively cheap fossil fuel power. But to make it into fuel is a different story. And here it does become very competitive, particularly if there are credits of it.
But that's a key component then, is getting the political will to make those credits there. So there is some incentive for those extra investments.
For sure. Well, you have to see it this way. Canada is a strong agricultural power, okay? You can either make your farmers be part of the solution, and that's what I just provided you some information on, or you can point fingers at them and say, well, look at all this environmental liability that comes from the agricultural sector. I am very clear that our farmers, just like our foresters, should be at the table because they are the only two sectors in society. They are the only two sectors in society that are not just a source for greenhouse gases, but also a sink for greenhouse gases. Just two numbers really quickly. In the United States, the EPA, the Environmental Protection Agency, says that agriculture and forestry are a source for 10.5% of our greenhouse gases. But if you read on their most recent emission inventory, you will find that agriculture and forestry are a sink for 11.8% of greenhouse gases. A source for 10.5, a sink for 11.8. Why do we never hear that? And why would we not want to further increase that sink function of agriculture and forestry?